All right. So as I mentioned, today's lecture talking about assembly and solution of finite element systems of equations, synthesizing all the different things that we've talked about. This title slide demonstrates the ultimate goal of moving towards trying to automate and solve these problems in sort of an algorithmic or computational setting. But don't let this title slide fool you. We're not going to start showing a bunch of MATLAB code in just a disconnected setting. We're going to be constantly referring to how exactly do we procedurally solve these problems. And certainly that's amenable to a computer doing a lot of the work for you. Or I think it's still valuable to understand how you yourself would do this if you had to do it yourself. So with that, let's review some of the details of what we talked about last lecture, specifically on the subject of assembling finite element stiffness matrices. And remember how we define stiffness matrices. They arose from our expression for the weak formulation of equilibrium. We came up with these integral expressions involving integrals of the product of different derivatives of the shape functions or the basis functions that we use to represent interpolated discretized versions of the solution field of interest, namely the displacement field. So we came up with these expressions that said I can assemble different contributions to my stiffness matrix by carrying out these integrals over the whole structure, or I can break up that integral into integration over each individual element. And I can carry out computations to determine what's the stiffness submatrix associated with a particular element. And then to determine the stiffness matrix for the whole structure, all I have to do is just sum up all of these element submatrices and put them in the appropriate locations of the resulting global or structure stiffness matrix. So my total stiffness matrix should have some number of dimensions associated with the total number of degrees of freedom or displacement unknowns in the structure. And the individual contributions to this global stiffness matrix are really just the summation of entries taken from the individual elements. And we also presented last lecture how exactly we computed these element level contributions to the stiffness matrix. We went through the derivation. You could carry out these element level integrals analytically if you had the time and the energy to do that, or we could apply these Gaussian quadrature formulas or numerical integration techniques to carry out those integrals in an automated fashion that only required that we provide some discrete number of integration points at which we can evaluate the integrand of those integral expressions on a per element basis. And we could then just come up with the integral as the weighted sum of those discrete integration point evaluations. So that was rather nice. The end result for this simple one-dimensional problem is that the resulting element local stiffness matrix looks a bit like this, something you're probably familiar with. It's just E times A divided by LE, the length of that particular element of interest, and then involving some small 2x2 submatrix with plus or minus 1 in most of the entries. So we could take each one of these sub-entries, plug it into the resulting global stiffness matrix in the appropriate locations, sum them together, and we get the global stiffness matrix. You've already done this. You've already even programmed this. Now, the other thing that we have to do is assemble the external forces, or kind of the vector filled with all of the external loads that would be applied at each of the nodes in the structure. And when you did this in the first homework assignment, you probably remembered if you had some distributed load, P, then in order to figure out how you converted this distributed load into an equivalent set of point loads, you had to use your intuition. You had to use your own judgment, and I encourage you to do that, to think about how exactly should I convert this distributed load into some equivalent set of point loads that I can apply to nodes 1 through 3 in this particular example. Now, given the way that we've attacked this problem in a slightly different way, we've set up these expressions for the resulting equivalent nodal forces that act at each one of these nodes. But the expression that we get is something that involves also an integral expression, much like the integral expression that we derived for this stiffness matrix thing. In this case, however, rather than involving derivatives of products of these nodal basis functions, now it involves actually the integral of the product of this distributed load function multiplied by whichever corresponding nodal basis function we're trying to kind of sum up contributions or nodal forces to. So we could do this same kind of summation procedure involving an integral over the entire length of the structure, or we could break up that integral, just like we did when we were summing contributions to the stiffness matrix, by considering contributions on an element by element basis. So this integral expression here involving the product of P times phi, one of the basis functions, we could do this over the whole structure, or we could break it up into multiple subintegrals. And we could carry out those subintegrals and determine what's the resulting contribution that each integrated one of these contributes to the resulting or attached nodes associated with that element. We also had potentially these concentrated loads, as we might have at this F bar applied to the right-hand end of the structure at node 3. If we have these concentrated nodal forces, then it becomes rather straightforward to figure out how exactly should I sum those contributions into the resulting vector of externally applied forces. All I have to do is take that load, apply it at node 3, and then stick it right into the third entry of this vector of externally applied forces. But what I want to point out is that these integral expressions involving integration over each individual element can also benefit from the use of numerical integration, rather than having to analytically integrate expressions that involve the product of these two, spatially varying functions, P, the distributed load, and N, let's say, the local shape function associated with one of the nodes of a given element. We could certainly work out that integral by hand, but that's cumbersome. And in general, if I have some arbitrarily defined distributed load function P, I might not necessarily know what I should do to integrate that ahead of time. So instead, I could come up with an equivalent approach to the way that we attacked the problem of integrating stiffness contributions, to instead just use this concept of numerical integration, Gaussian integration. So to do this, I have to first transform my integral, which is expressed in terms of the global coordinates of the structure. It's an integral over x1 to x2 for a particular element of interest. And I can transform that integral from x ranging from x1 to x2 into an equivalent integral over the element's parametric coordinate domain, where that parametric coordinate is nothing more than that xi, which ranges from xi equals -1 to xi equals +1. And we had to do this sort of change of variables formula to be able to convert everything into, rather than integrating over x, integration over xi. We do that, we can apply our Gaussian quadrature formulas to instead convert this integral, or rather approximate this integral, through some weighted summation of discrete evaluations of the integrand, P and N multiplied together, but evaluated at these discrete quadrature point locations, xi1 or xi2 in the case of a 2-point Gaussian integration scheme. And we can just go ahead and evaluate these functions, sum them together, and we can come up with what are those weighted contributions to the overall nodal forces that act at the nodes of this particular element. We could do this on an element by element basis. We can get individual contributions. We can sum them all together and consolidate them into one big, vector of all of the resultant forces that act at all the nodes in the structure. So summing contributions on an element by element basis, summing contributions that come from any discrete or concentrated nodal forces, and then putting them into this final array. Now that we've done this, and not to kind of like jump through it, but now that we've done this, really the question becomes, how do we actually work with this final answer? We've assembled a stiffness matrix, by summing up contributions to it. We've assembled our kind of vector of externally applied nodal forces, or equivalently lumped nodal forces. Now we come to the problem of solving for the actual displacements of the structure, or the nodal displacements. How do we do this? We've set up this system of equations that looks kind of like this. Ku equals F external. Or in other words, the stiffness matrix times the vector of unknown nodal displacements equals this vector of externally applied nodal forces. Now, it's tempting to say, let's just invert this stiffness matrix, and then we can solve directly for the nodal displacements. But there was that extra step we had to deal with, right? What was that extra thing we had to do to modify this system of equations before we could actually solve for those individual unknown nodal displacements? Remind me, what did we have to do? Yes, exactly. We have to enforce the boundary conditions. And in particular, we have to enforce this displacement boundary condition, which was equivalent, at least in that simple example that we considered, homework number 1, the second lecture. All we had to do, if we knew that this support remained stationary, such that this node didn't displace or move anywhere, then all we had to do to solve this problem was just eliminate the corresponding row and column from the stiffness matrix and eliminate this kind of entry and just kind of treat that as an unknown. It's a support reaction that we're going to solve for later. And then all we end up solving for is this reduced 2x2 system of equations to solve for the resulting 2 nodal displacements at x2 and x3. Now, I want to come up with a slightly more general procedure for how we solve those kinds of problems, and I'll illustrate exactly how we do that. But I also want to connect everything together and present this whole procedure of assembling the stiffness matrix, assembling a vector of external forces, and doing this, solution procedure given the assembled stiffness and force to come up with the solution for the displacement field. So how do we do this? All right. Well, in general, you can attack any one of these problems in a fairly generic step-by-step procedure. And this applies not just in the case of these very simple one-dimensional, types of problems, but it generalizes actually quite nicely to any type of finite element procedure. Behind the scenes, most finite element codes are doing something roughly equivalent to this. You yourself have to do a lot of this first step, defining the problem that you intend to solve. But the rest of these, 2 through 6, that's the thing that your finite element program is doing. So understanding what these steps entail and what are the hiccups or the points where maybe your finite element program might encounter some error or might have some issue that you have to address. It's useful to know what's going on so that you can at least try to diagnose, maybe I set up my problem wrong or something. And maybe that's what's causing the rest of this problem to blow up or something else. All right, so we'll go through this step by step, and I'll give you some perspective on how exactly we might define these different definitions for the primary quantities of interest in a finite element program by giving you an idea of what are the primary computational objects, as it were, that are of relevance to these finite element programs. And we've already talked about most of these. There's nodes, those discrete points at which we have attached degrees of freedom, characterizing the displacement at those individual discrete points. We have elements that are connected to these nodes in general, and within each element, we might assign some material properties or other kinds of properties that characterize how this particular element might deform and what's its stress-strain response. We can also impose things like boundary conditions, either displacement or force boundary conditions, and we can apply like distributed loads, either body forces or other things like that. So when it comes to defining nodes, we can just characterize all of the nodes in the structure simply by listing them off, and more specifically, listing off their specific nodal coordinates. And in addition to that, we're also going to adopt an indexing scheme. In order to be specific about which node is which, we have to attach this node index to nodes 1 through 5. And we've already kind of implicitly been doing this, but let's be more precise about this and consistent in saying that anytime we define a new node, we have to assign it a unique integer index, 1 through 5 in this particular example. If you wanted to do this in a computational setting, I'll present alongside a lot of these definitions, which are somewhat generic, and how you might attack this problem in using pen and paper. If you were to do this in a computational setting, you might define all the different nodal coordinates, x, where x ranges from x1 to x5, just by defining their specific nodal coordinates, kind of like shown here. So this particular example is actually taken from a simple MATLAB script, which I've actually uploaded to Canvas. So if you like, after this lecture, you can take a look at precisely all of these steps put into sequence in the context of that MATLAB example. And it might be a little bit helpful to just kind of reconcile what we go through here with what appears in that script. Okay. So we can define all the nodes just in terms of the nodal coordinates. We can assign to each node a particular node index. And to define elements, an element really is nothing more than just some subsegment of the overall structure, but which is end-capped by two specific nodes. And to define an element, all we need to do is just define what's its nodal connectivity, or which nodes constitute its specific endpoints. We can list off this connectivity in the format of an array that looks something like this, where if I wanted to define element number one, all I have to do is define what its nodes are. In particular, what are its corresponding nodal indices. So element one has nodes 1 and 2, corresponding to this first row. Element 2 has nodes 2 and 3, corresponding to this second row. And element 3, as shown highlighted, has nodes 3 and 4. So if I want to define elements, I can do so just by defining their connectivity. In addition to that, I also have to assign material properties to each element, which might be different. Similarly, I could assign things like cross-sectional properties to a given element. And I could do that, assemble it in just an ordered array. And similar to the way that I'm defining nodes, I can assign an element index, a unique integer identifier to each one of these elements, just to kind of keep things consistent. All right, so I have elements consisting of just their nodal connectivity, or kind of associating them with those unique nodal IDs. I also have their resulting cross-section properties that I might assign, and any material properties that are associated with each element, which could be different. All right. The other thing that I have to define are boundary conditions. Which nodes am I actually constraining? And in a lot of the problems that we've been talking about, it's assumed that I can only really constrain these end nodes, right? Let's say node 1 or node 5. There's nothing that says I couldn't come and just, pinch node 3 and prevent it from displacing. So theoretically, I could identify any one or multiple of these nodes and prescribe exactly what is the displacement at that node. To do that, I have to define nodal boundary conditions or displacement boundary conditions. And usually that entails identifying which specific node IDs am I going to constrain. And for each one of those specifically constrained node IDs, I have to prescribe what is the imposed value of the nodal displacement at each one of those different values. You can make it a little bit more compact if you like. You can basically just list off what are the IDs of the constrained nodes and what are their corresponding displacements. I could put that in this kind of simple format in terms of these kind of like sets or vectors or arrays of indices and corresponding imposed nodal displacement values. Or I could define these arrays in, again, also a MATLAB context. So kind of simple. What about externally applied forces? Well, if I'm applying concentrated nodal forces, I could adopt the same scheme. If I know that there's some concentrated forces, let's say at nodes 2 and 4 that I need to impose, then I can just say, well, list off the IDs at which I'm applying these concentrated nodal forces, and then just define what are those forces in, again, arrays that you could define like so, or in a MATLAB context equivalently. Fairly straightforward. Okay. Now, beyond that, I might also want to apply, let's say, a distributed load, which might have some variable force per unit of length that's applied along the length of the entire structure, such as, let's say, P as a function of X. And I could define that function as really any possible function I like. It could be a linear function, as shown in this example. It could be, some kind of weird discontinuous function, sinusoidally varying function. It's whatever is characteristic of the applied loading that you intend to put on the structure. But at the end of the day, you could define it as just some generic function or having a particular form. In a MATLAB context, let's say, if you wanted to define a function, this is sort of an odd concept. But MATLAB actually allows you to define a function as kind of like an argument to this particular expression. So P in this case, when you use this funny syntax with like an @ symbol and a parentheses X, it basically means that I'm defining P to be a function that I can come back and evaluate by basically saying P parentheses X. It'll allow me to actually evaluate P at a particular value of X. And in doing so, it will actually use whatever expression you've defined here. So for example, for this linearly varying function, I can define P as just this linearly varying function of X. All right, kind of an interesting concept. This is actually something called a function handle in MATLAB. So kind of a fun idea. It gets used in that script that I've shared on the Canvas webpage. So you can kind of take a look and see how that gets used. Other than that, we've set up the problem. We've defined all of the different things that we need, the nodes, the elements. We've defined the boundary conditions. We've defined any ancillary information we need, nodal indexing schemes, element indexing schemes. Now we can actually come to the problem of solving, or rather assembling, the resulting system of equations that comes about from establishing our weak form integrals. All right, so the first step that we need to do, actually, it can be broken down into multiple steps. But the first step involves assembling the stiffness matrix. You've already kind of done this, and I think many of you have taken this approach. But you start by just defining a stiffness matrix that is all zeros. So initialize it to all zeros and dimension it such that it can contain all of the degrees of freedom in the problem, regardless of whether you've constrained some of them or not. So in this case, the rows and columns indices of this matrix directly correspond to the node indices as I've defined in my original problem. If I had somehow decided to be a little bit funny and I said, this is node 1 and this is node 2, and then this is node 3, that's perfectly admissible, but you have to just keep track of those things. It becomes more of a bookkeeping game. Ultimately, it's up to you to decide how you're going to order the particular nodal degree of freedom indices, but it will influence what the resulting form of the stiffness matrix looks like. So you have to keep those things in mind. All right, to actually assemble the stiffness matrix, again, this is recap. You've already gone through this exercise. All you have to do is loop over each individual element, compute what is the local stiffness matrix associated with that element, and then sum that resulting local stiffness matrix for that element into the global stiffness matrix for the whole structure. So for example, if I were to looping over these different elements in the structure, starting with element number 1, I can compute what is the element local stiffness matrix, that small 2x2 array, and I can determine how it should fit into the appropriate locations of the global stiffness matrix by noting the nodal connectivity of this particular element. So element number 1 has nodes 1 and 2, which means that I'm going to be summing these entries into row and column 1 and 2. Similarly, if I go to element number 2, which has nodes 2 and 3, then this small 2x2 stiffness matrix entry would get summed into the corresponding rows and columns 2 and 3. Fairly straightforward. And that continues for obviously elements 3 and 4. And you'll notice something interesting in terms of how this stiffness matrix gets filled in. So you might have encountered this, maybe you even noticed this when you were doing homework assignment number 2. But as I increase the number of nodes, or the number of elements, if you like, in this overall structure, I start to see kind of a pattern. As I increase the number of nodes or elements, the format of the stiffness matrix, assuming just linear indexing from left to right, numbering the nodes in that sequence, I'll get a format for the stiffness matrix that's nice and compact, or basically only has, non-zero elements along the diagonal entries, or rather the tri-diagonal entries of this stiffness matrix. That's really cool. And actually, this format and that consequence actually comes about precisely because of the way that we've constructed our basis functions. Using finite element basis functions gives us a format for this stiffness matrix that has these interesting properties. It's sparse in the sense that not all of the entries of the stiffness matrix are non-zero. Some of them, all of these kind of boxes that are just represented as white, empty cells, those are all zeros, basically. Only these blue entries along the diagonal are non-zero. And that sparsity basically means that if I wanted to store all of this information to represent this stiffness matrix in a computer's memory, then I only have to store these non-zero values. And you can imagine the benefit of that if you scale up the size of these problems of interest to include not just, 10 nodes or so, but maybe, I don't know, millions of nodes. What if you had a structure that consisted of that many nodes? The number of non-zero entries in the stiffness matrix actually doesn't scale up that poorly. I mean, in the end, it'll be still proportional to the number of nodes, but you won't have to store n by n potentially non-zero entries. So that kind of sparsity property is really useful. The bandedness property is also useful for the sake of efficiently solving these problems. And there are specific solution strategies that you can apply to invert or solve these systems of equations if they do happen to have this particular banded format. So finite element stiffness matrices actually have a lot of really nice properties from a numerical linear algebra standpoint. So that's an interesting observation that we can take away from this, is just, finite element stiffness matrices really are efficient from a computational standpoint precisely because they possess these properties. All right. Now, we've assembled the stiffness matrix just by looping over all the elements, summing individual element stiffness contributions. What about the external force vector, the vector filled with all the external loads that we want to apply to all the nodes? Well, we can do kind of a similar procedure. We can initialize that vector of external loads. Suppose initially that there are no forces, and we're just going to go around and sum all the different contributions into this, external force vector. So initialize it to 0, give it 5 different 0 entries initially corresponding to the individual 5 nodes in the problem. I can then look at any concentrated loads that I might be applying to the structure. Let's say at nodes 2 and 4, all I have to do to apply those nodes in this external vector of forces is just sum those contributions directly into the corresponding entries of the external force vector. The next step is to just integrate contributions from whatever distributed loads might be applied over the whole structure, involving that distributed load P, which might vary as a function of X. It could be a generic function. It could be, some MATLAB function handle that we've defined in a computational setting or something like that. But remember, in order to evaluate those contributions and sum them to the corresponding entries in this vector of external forces, we have to compute these integral expressions involving the product of that spatially varying function P, the distributed load function, multiplied by the shape functions of each individual element. And we could do that by integrating over the whole structure, or as we'll do in this example, we do it by computing these integral expressions on an element by element basis. So we loop in a similar fashion as when we assembled the stiffness matrix, we loop over the individual elements. And then for each element, we carry out these integrals to determine what's the integral product of this function multiplied by the corresponding nodal shape functions for that element. We determine what are the equivalent lumped nodal forces from this distributed load that should be applied at the corresponding nodes 1 and 2 of that element. So kind of just briefly to illustrate, if I had element number 1 with nodes 1 and 2, I could integrate this expression. I could do it analytically, or more likely, I could do it using numerical integration, converting these integrals over the element into equivalent, discrete evaluations at the element's integration points of interest. And I could evaluate these different integrand contributions involving the product of P with either node shape function 1 or node shape function 2. And that effectively gives me the equivalent lumped nodal force that gets applied at node 1 or the equivalent lumped nodal force that gets applied at node 2 caused by that distributed load P. I could do this for element number 1. I could sum up these resulting contributions into the corresponding entries of the external force vector. I could then just loop over the rest of the elements and do basically the same thing. And assuming that I'm using Gaussian integration, then doing this isn't so bad. I can just say, define what is that special function P, maybe as a MATLAB function handle, and I can carry out these integrals fairly easily, at least in an automated numerical context. Sum up all these different contributions into the corresponding entries of the external force vector, and then I finally arrive at my assembled external force vector, including discrete nodal values of concentrated loads applied to individual nodes and distributed loads integrated on an element by element basis. Now, the last thing I need to do is set up all of my boundary conditions associated with constrained nodal displacements. So initially, I have to actually kind of come up with a guess of what I think the nodal displacements are going to be. I don't yet know what they are, they're unknowns in this problem. But if I want to set up the problem in a consistent way, I could just guess. Well, just assume that the structure doesn't displace at all. So impose zero displacements everywhere. I could then come back and say, well, actually, I happen to know that I am constraining, let's say, nodes number 1 and number 5. So in order to impose those constraints, I should come back and I should really say what those nodal displacements are. I'm imposing them. So if I'm constraining nodes 1 and 5, I can impose those nodal displacements by just taking those prescribed values and putting them into the appropriate locations of the nodal displacement vector. And then finally, once I've done all this assembly process, I've set up, the stiffness matrix, the vector of external forces, and I've even kind of populated my vector of nodal displacements with whatever prescribed values I have. Now the question becomes, how do I solve this system of equations? Coming back to the question that we started with, I have this system of equations that looks like KU equals F external. And I happen to know, rightly as you put it, that we need to have some enforcement of these boundary conditions, which, if you remember, entailed eliminating whatever rows and columns were associated with the constrained degrees of freedom in this kind of system of equations. Now, I want to point out that for whichever of these nodes that we are constraining, let's say nodes 1 and 5, then the resulting reaction forces that occur at nodes 1 and 5, let's call them F1 and F5, kind of denoted with this purple color, that those are effectively unknowns in our problem. If we're prescribing displacements at those nodes, we also kind of have to treat the resultant force that acts at those nodes as an unknown of the solution that or of the problem that we're solving. So in effect, even though we're trying to eliminate these displacement unknowns from the problem that we're solving, in doing so, we actually introduce these additional force unknowns. So that's kind of a tricky thing that we need to deal with. But in the end, what we have is that we have these 3 unknown displacements that we need to solve for, U2 through U4. And we have these 2 unknown reaction forces that we have to solve for, F1 and F5. But otherwise, I suppose that I know what U1 and U5 are, and I suppose that I can kind of count on F2 through F4 as being just whatever forces I previously computed by doing that summation procedure, by summing contributions from concentrated nodal forces and from whatever distributed forces I might impose on the structure. Okay, now the question becomes, well, exactly how do we solve this problem while accounting for this set of constraints? And the trick in doing this is kind of equivalent to what I had described previously, nominally eliminating those particular rows and columns of the system of equations corresponding to the constrained degrees of freedom. But I could also be a little bit funny in how I attack that. I could eliminate those rows and columns, or I can take an approach that kind of looks like this. Rather than eliminating those rows and columns, I can just rearrange the rows and columns of this resulting system of equations and reorganize the displacement unknowns and the resultant forces into a slightly different format that might look something like this, where I've organized actually the stiffness matrix into these subarrays, at the same time as I've also reorganized the entries of the displacement vector and the vector of external forces to be, consisting of the vector of all of the displacement unknowns that are free degrees of freedom, or the things that I'm solving for. And in this kind of lower portion, I can consolidate all of the imposed, constrained displacement degrees of freedom in this kind of subvector here. Similarly, I can rearrange all of the entries of this force vector into the external forces that are applied at these corresponding free degrees of freedom in the structure, and also all the unknown support reaction I can bundle into this submatrix on this kind of lower end. To give you a little bit more of a tangible view of exactly what does that look like, suppose I had my original system of equations consisting of the stiffness matrix, the vector of nodal displacements, and the vector of kind of forces. Now, I know nodes 1 and 5 are constrained, and I know that the forces applied at nodes 1 and 5 are effectively unknown reaction forces. So in order to do this transformation, I want to rearrange or basically permute the rows and columns of this whole system such that I can kind of basically renumber all of these different nodal displacements and kind of position them in this format, where all of the unknown nodal displacements are kind of in this first half, and all of the known nodal displacements I put in the bottom half. I do kind of the same thing with the force vector. And at the same time as I do these transformations for the displacement and force vectors, I also have to rearrange correspondingly the entries of the stiffness matrix just to make things consistent. So now you can kind of see, if I've partitioned this system of equations in this following format, then effectively I can repose this whole problem of solving for these currently unknown nodal displacements as basically solving a subsystem of equations that involves just this kind of 3x3 system of the stiffness matrix involving these 3 unknown nodal displacements and involving these kind of 3 imposed external forces applied at nodes 2 through 4. So at the end of the day, really what I want is to solve this partitioned system of equations to determine first, what are all of those unknown displacement degrees of freedom in that kind of upper half of this, those 3 values, U2, U3, and U4, which involves really just using those sub-partition blocks of the stiffness matrix, that 3x3 stiffness subarray, and solving for what those resulting unknown displacements are. It's kind of equivalent to just saying, in this context, eliminate these kind of corresponding rows and columns of the stiffness matrix, and then treat it like you're only solving this smaller subarray. That's effectively what this first step is doing. Solve for that kind of small 3x3 subsystem of equations for the unknown nodal displacements. However, I still don't really know what are the resulting external reaction forces, F1 and F5. But if I've done this first step, if I solve that smaller 3x3 system of equations for U2 through U4, then I can come back, plug it into the global stiffness matrix, and basically recover what those reaction forces are, which is effectively what this second step is doing. Once I know what all the 3 degrees of freedom displacement values are, and I already kind of knew what those constrained displacement values were, I can plug them back in and use those partition subblocks of the stiffness matrix to just directly reconstruct what are those support reaction forces. Okay, so that's effectively what this is doing. In MATLAB, it actually looks really, really simple. It involves basically doing this inversion or matrix inversion operation, which at the end of the day, we could go into all the details of exactly what's happening behind the scenes in inverting a stiffness matrix or solving these systems of equations. We might talk about that, but for now, it's sufficient to just tell you that MATLAB has a very efficient and convenient way of doing that, and it's just built directly into this / operator. If you're already familiar with matrix methods and matrix inversion procedures, one particular means of inverting a stiffness matrix is something called Gaussian elimination, not to be confused with Gaussian quadrature. Gaussian elimination is really just a sequence of elementary row operations where you're kind of augmenting the system of equations you're solving in order to figure out what the resulting values of, let's say, the displacements are in this kind of system of equations. So it's really no different from making some substitutions and kind of solving things as you might by hand. It's just a little bit more systematically organized. And in particular, there are plenty of automated computational techniques for inverting stiffness matrices and doing things like that. So really cool. So at the end of the day, this is, in spite of the apparent simplicity of the resulting expressions and the corresponding implementation of these concepts in this automated, computational setting, this is probably where you would have otherwise had to spend most of your effort in solving these problems. This is where you're kind of like crunching through numbers and trying to like solve these systems of equations. It takes a lot of time. But the nice thing about these methods is that if you've implemented everything in this computational setting, Now you can just let the computer do the work for you. You can just have the computer invert the stiffness matrix. And even though it still can be, in some cases, a really computationally expensive procedure, especially for really large problems, it's nonetheless a much more trivial task for the computer to do it rather than for you to do it. So truly a powerful technique. All right, so now that we've done this, we've determined what are all of the corresponding unknown degrees of freedom or displacements in the structure at these internal unconstrained degree of freedom locations of the nodes. We've also reconstructed what are the support reaction forces. Now we can come back, we can figure out on an element by element basis, knowing what the resultant displacement of the nodes are, I can come to each individual element and I can figure out what are its internal states of strain, stress, and internal force. In the case of these simple one-dimensional problems, it's fairly straightforward. It uses a lot of the same formulas that we had discussed early on in the class. So we don't have to belabor that. I think we can kind of just skip over this. The only thing you really need to know is that if you're trying to recompute all of these intermediate values, you do have to go loop over all the elements, figure out which nodal displacement should be passed off to which elements by using that same kind of nodal indexing scheme and the elements connectivity array. All right. Finally, the fun exercise that I think we have a little bit of time to, focus on before we end the class today is actually running some problems and visualizing and interpreting the results. So to kind of showcase some of the capabilities of that script that I shared on Canvas, I've concocted a few specific problems that I'll invite you to ponder what the resulting solution should look like, just based purely on your intuition. We'll solicit some of your thoughts on what you think the resulting solution for the displacement field should look like, what the resulting solution for the internal force distribution in this structure should look like, and then we'll actually give you the answer. So I have 3 of these examples we can work through, but let's start for this kind of simple one. It's just a 2-element problem. I'm constraining this support here, imposing 0 displacement, and I have 2 elements. There's an end force applied at the right end, and I have some slightly different properties assigned to each of these 2 elements. They both share the same cross-sectional area. The only difference is that this element is a lot softer, let's say, than this element. So this element has a much higher stiffness by a factor of 10 compared to the element on the right. So considering those details, if I had to kind of get your guess, what do you think the resulting solution for the displacement field, what should it look like for this structure? All right. What do you say? What should it look like?
The straight line up to the first, yeah,
Something like that? Yeah.
and then more steep.
Like a steeper line, I guess, for the second half. Let's say if this is nodes 2 and 3, then your guess is something that looks kind of like this. Is that right? Okay. How do you all feel about this? I see a nodding head. Yeah, maybe. Okay, some nodding heads. Okay. All right. Well, if that's the case, what about we still have 5 minutes. All right. What about the internal force? How do you think the internal force should vary in this assembly as a function of position? I think you're saying like just kind of straight across. You're saying maybe downward sloping. Other thoughts? Well, I'll invite you to kind of use your classical intuition and classical methods of analyzing structures to think about what would happen if I were to cut through any arbitrary section of this structure. And if I were to measure through some method of sections, what's the resulting internal force that would act across that internal cut? Using that logic, what do you think the internal force should look like as a variable function of position? I think maybe you had you're kind of like, yeah, just basically it's constant. is kind of one way to, as kind of how I'm interpreting a lot of the visual depictions that you're presenting. So I would agree. So we expect the internal force should be constant over this whole structure, right? So in both of these elements, we expect the same internal force. We expect that the displacement field might look something like this, potentially. But isn't this odd? Like we have constant internal force, but kind of variable displacement, or at least variable strain, if you like. If this is truly what the displacement field looks like, then it would certainly imply that the slope of the displacement field, or the derivative of the displacement field with respect to x, is basically the strain field. So in other words, we expect, more strain in this element compared to this one, but it's the same internal force. Well, it is true. All of these things can be true at the same time. And in this particular example, we do have exactly this variation, very good, of the displacement field. The strain will look discontinuous. That's an interesting observation. It basically says that right at this point, this junction between these two kind of differing materials, there will be this very sudden jump in internal strain. And that's caused precisely because of this mismatch in the stiffness properties of those two materials. In spite of the fact that they have, the same cross-sectional area, everything else is the same. But the internal state of stress, and in fact, the internal state of force, is still a constant over the whole thing. And simply that has to do with that discrepancy of, well, if I have some distinction between E1 and E2 being different, I still have to satisfy equilibrium, which is what these equations are ultimately solving. They're enforcing equilibrium in this kind of weighted integral average sense. So we still have to satisfy equilibrium, but we still have to satisfy other things like compatibility and whatnot. So at the end of the day, this is totally admissible. And in fact, this is the exact answer. If you were to try to solve this problem, with a larger number of elements, you'd get the same answer, basically. It doesn't change, actually. So here's another example, similar to the last one, except in this case, rather than having differing values of the Young's modulus, I have differing values of the cross-sectional area. All right, what do you think about this one? Same? You say same? So maybe something that looks like this for the displacements? I see some nods. So kind of a similar concept, we should expect, this discontinuous variation in the displacement, maybe the discontinuous jump in the internal strain. Internal force, you think this should still remain constant? Well, internal force, internal revolvement force, yeah, I would say it should still remain constant. I mean, at the end of the day, we can cut through either one of these two members. It'll have the same internal force. What about, rather than internal force, what about stress? Force per unit of area. Should it also be constant? No. Yeah, clearly, because it should look something more like, well, what should it look like? Which one of these elements has the larger stress? Yeah.
It's going to be a piecewise.
Something like that, maybe, and possibly discontinuous. Yeah. Yes, in fact. So you can rationalize a lot of those things just based on your intuition, which is really critical. I want to emphasize this, that this isn't just, kind of like a fun exercise. This is something that you should always approach any kind of finite element program with the mindset that you can't always necessarily trust the outcome of what you're going to get from the analysis. And it's not necessarily because the finite element program is wrong or doing something inherently bad. It could be that you just goofed up. You just defined your problem incorrectly, and you have to go back and revise some of your assumptions and the way that you set up the problem. If you're not getting an answer that you expect and that you can apply your intuition to kind of rationalize, I believe this answer, then you really should, revisit some of your fundamentals and kind of feel like you have a good, solid understanding of what you expect the answer should be and apply that understanding to try to validate your answers. All right, so in fact, all the things that we talked about, you're all right. We'll have a discontinuous strain field. The displacement field will still look like this. The stress field will be discontinuous, but the internal force will be constant. All right, the last one that I'll leave you with is really the same problem that I gave you for homework assignment number 2. So you already know what the answer should be. You've already kind of gone through the exercise, right? It was a constant material and cross-section properties just with this constant distributed load. So I'll kind of just give the answer. It's basically just this, nice, it should be a nice smoothly varying displacement field that looks kind of like an upside down parabola. Interestingly, though, the strain field, the stress field, even the internal force field look like these piecewise discontinuous functions. What's the deal with that? You might have plotted this in your homework assignments and kind of presented your answers in a variable format, but really, if we're being true to the way that we're representing the variation of these different fields on an element by element basis, then really the answer that my finite element program is giving me tells me that for some reason there's these jumps or discontinuities in the internal force field, which kind of looks a little weird. And it's kind of hard to rationalize why that is. Now, I would encourage you, in advance of the next lecture, to reflect on this and ask yourself, why is this happening? What is this something that we should be concerned about? You've already kind of thought about this probably in the context of homework assignment 1, but I want you to revisit that assumption now that we've gone through all the mathy details of setting up the finite element analysis to begin with, analyzing things in terms of displacement fields and functions as the solutions that we're seeking, but also noting that these solutions are simply approximate solutions to the original problem that we sought to solve. We're only able to solve these problems in an approximate setting based on the way that we've chosen our finite element basis functions. And though these basis functions give us the best approximation to what the true solution should be, they're nonetheless an approximation. All right, so ponder that in advance of next lecture, and we'll resume on Monday. But yeah, anyways, feel free to visit me in office hours if you have additional questions, but otherwise I'll see you then.